All right, let's jump right in. We're going to tackle a question that's at the very heart of chemistry. What is actually going on when things react? We're going to break down that invisible energy dance that decides if a chemical reaction feels hot or, surprisingly, cold.
So think about this for a second. You're sitting around a campfire, right? And it's just throwing off all this warmth. But then you twist an instant ice pack for an injury and it gets shockingly cold. I mean, both are just chemical reactions. So why the totally opposite effects? That's the exact mystery we're going to solve today.
Okay, to get to the answer, we have to start with the most basic rule of the game. You can think of a chemical reaction as basically a giant game of atomic musical chairs. And that's really it. There's no magic happening here. The very same atoms you start with are the same ones you end up with. They're just rearranging, breaking away from their old partners to hook up with new ones, forming brand new substances with totally different properties. Now, for this big atomic shuffle to happen, something has to give. The very first step in pretty much any reaction is breaking things apart. And that always comes with a price, an energy cost. And the things that need to be broken, we call those chemical bonds. These are just the fundamental forces that hold atoms together, creating all the molecules that make up, everything around us. Thinking of bonds as glue is probably the perfect way to picture this. It's the stuff holding atoms together in a connection that's actually pretty strong, and it takes real effort to break it. And this right here is a really crucial point. You can't break this atomic glue for free. You have to invest energy. The reaction literally has to absorb energy from its surroundings just to get going, just to pry those atoms apart from each other. You can almost picture it happening, can't you? As that energy flows into the molecules, they start to vibrate and shake more and more violently. They get super unstable until, snap, the forces holding them together just can't take it anymore, and the bonds break. So we've paid the energy cost, we've broken the old bonds, but now we get to the second half of the story, the reward. This is the energy payoff that happens when new, more stable bonds get formed. See, once those atoms are free, they find new partners really fast, and when they lock into these new, more stable arrangements, they can exist at a lower energy state. They just don't need as much energy to hold themselves together. So all that leftover energy, it gets released, usually as the heat and light that we can actually feel and see. That's the payoff. Okay, so now we have our two key puzzle pieces, right? Energy goes in to break bonds, and energy comes out when new bonds form. With just that, we have everything we need to solve our original mystery. So here it is, the two possible outcomes. If the reaction releases more energy forming those new bonds than it took to break the old ones, you get a net release of energy. We call that an exothermic reaction, and it feels hot, just like our campfire. But if it takes more energy to break the original bonds than you get back from forming the new ones, the reaction has to keep pulling energy in from its surroundings. That's an endothermic reaction, and it feels cold, just like that instant ice pack. We can tie all of this together with one simple, really powerful visual. Just think of the entire reaction as a journey over a hill. Just picture it in your mind for a second. The molecules you start with are at the bottom of a hill, and for them to react, they have to get all the way over to the other side. So here's how that little journey works. First, you have to push the molecules up the hill. That's the energy you have to put in to break all those old bonds. At the very peak of the hill, the molecules are in this super unstable moment called the transition state. Think of it like the tipping point, where the old bonds are broken, but the new ones haven't quite formed yet. And then, as the new, more stable bonds snap into place, the molecules get to roll down the other side, releasing all that energy on the way down. So, after all that, what is the one thing you absolutely need to remember from this whole explainer? Let's boil it all down to its simplest form. It all just comes down to a balancing act. Energy goes in to break bonds, energy comes out to form new ones. And it's simply the difference between those two that decides the entire energetic fate of the reaction. It's a really elegant and powerful principle when you think about it. And that simple exchange, it's not just for campfires or ice packs. It's the engine that runs underneath, everything. It powers the metabolism in our own bodies, it drives photosynthesis in plants, and it fuels the fusion reactions inside stars. So the question I want to leave you with is, now that you know what to look for, where else in your daily life do you see this fundamental energy exchange at work?